Hello. We're going to begin chapter 14, which is all about vibrations and waves. And so today we're going to talk about section 1, which is periodic motion. And so looking at waves and how they repeat and things like that. So periodic motion is motion that repeats in a regular cycle. So an example of this would be a pendulum or a guitar string. So something that will go back and forth at a regular pace. Usually things that have periodic motion have one position where the F net is 0, and this would be when it's at equilibrium. Periodic motion can also involve specifically simple harmonic motion, and this is if the force that restores the object to equilibrium is directly proportional to the displacement of the object. So we don't mean equal, but if the force has some relationship to the displacement. And there are two parts to this. The first part is the period, which if you remember from before is a capital T. And this is the time needed for the object to repeat one complete cycle. So for a guitar string, it's the up and the down and then back to the equilibrium position. That would be one cycle. The other part of simple harmonic motion is the amplitude, and this is the maximum distance the object moves from equilibrium. So for example, let's say that we have a wave, a guitar string for example, that was plucked. It's going to go up and down and follow a type of simple harmonic motion. This dashed line represents our equilibrium, and the distance from the equilibrium point is our amplitude. So for example, from here to here, and for example, from here to here. Now, if this were drawn to scale, you would see that those amplitudes would be the same distance from the equilibrium. Okay, well, we can also relate this to springs, because if you pull a spring and you let it go, it tends to go back and forth until it reaches equilibrium or stops moving. And so there's a specific law that goes along with this called Hooke's law. Okay, and Hooke's law says that the force exerted by a spring is directly proportional to the amount that the spring is stretched. And so the more we stretch it, the more force exerted. Okay, well, we also have an equation that represents Hooke's law. So F is equal to negative kx, F representing our force. K is what's called the spring constant. This depends on a lot of things. It's kind of like the coefficient of friction. Depends on the stiffness and other properties of the spring. And then X represents the distance that the spring is stretched from its equilibrium position. Equilibrium usually being, if you just held the spring up, it wouldn't be stretching any, and then you would apply that force to stretch it. So springs that obey Hooke's law are considered to be what are called elastic. Okay, we can also look at the mass on a spring and relate that to potential energy. And so potential energy of a spring is equal to 1/2 times the spring constant times the distance that the spring was stretched, that value squared. And so the net force of the spring depends on its position. So if we have the spring and then we hang an object from the spring is going to stretch because we're applying that force, and it'll stretch until the force of the spring is equal to the force of gravity in equilibrium. If you pull the object down, the force of the spring will increase until it balances out, and then in that case it would be the force due to height plus the force due to gravity. I think this got cut off here, but that should be, whoops, not that way, a G. If I have my spring and I apply a weight to it and I pull it down, when I let it go, it's going to accelerate up. Obviously, the stretch will be reduced and the force net is going to decrease. Once it reaches the equilibrium point, acceleration and F net are 0, and it's going to have a constant upward velocity, so it's going to move upward. And then it's going to return, or it's going to start moving with simple harmonic motion until it returns to the equilibrium position. So I've pulled my spring down, I let it go, it bounces up, and then it's going to continue to go up and down until it returns to equilibrium. The period of oscillation, that capital T, or the time it takes to do one full cycle, depends on the mass of the object and then also the strength of the spring. Okay, so we can also take this idea and relate it to automobiles or cars. So a car's ability to retain its shape in a crash, which is important, depends on how much kinetic energy initial, since it's moving, is transferred to the elastic potential energy final of the frame. And so we want to retain our shape. So a bumper on a car is basically a modified spring. Its purpose is to kind of cushion a lot of that energy or store a lot of that energy so that the occupants of the car don't feel it as much or the shape of the car is not deformed. When the car stops, the spring is compressed, right, the bumper, and hopefully that prevents the car from being deformed. The spring then returns to equilibrium and the car recoils off of whatever it collided with, which is going to be a better result for the people inside. Pendulums are also an example of simple harmonic motion. So a pendulum has a massive object, which we call a bob, suspended by string or a light rod of length L. So L here would be small l. So usually you have some sort of a string. Whoa, where'd it go? A string with an object, and then you would pull it back, and then basically it's going to have this harmonic motion back and forth. So the string or the rod exerts a tension force, because remember, tension force is the force due to a string, and gravity exerts a force of F of G on the bob. So we have the tension and then force due to gravity. So the vector sum of these two forces is what produces the net force. And we can have three different positions for a pendulum. So the first two positions are the left and right. So the maximum to the left and the maximum to the right that the pendulum has been taken, so depending on how high you pull it up. Here, F net and acceleration are maximum, and velocity is 0. At the middle of its rotation, F net and acceleration are going to be 0, and velocity is maximum. So that F net is a restoring force that puts it back at equilibrium. We can also look at the period of a pendulum, or the time it takes for it to do one full rotation. Okay, so depending on where you start it from to go and come back. So the period is equal to 2 pi times the square root of L over G. So 2 pi square root of L over G acceleration due to gravity. L representing the length of the pendulum and G representing the acceleration due to gravity. Okay, so we've been talking about simple harmonic motion and things going back and forth, and this also relates to resonance. So this occurs when small forces are applied at regular intervals to a already vibrating or oscillating object, and because of this small force being applied, the amplitude or the amount of the vibration increases. And so the time interval between the applications of force is what's called the period of oscillation. And so how often is it between when you're pushing on this object or however you're applying a force? This is a special form of simple harmonic motion. And those additions of the small amounts of force at specific times in the motion of the object can cause larger and larger displacement. So that's why it's a form of simple harmonic motion, because we don't have the same repetition, but we have that same idea. We're just applying these forces and causing that displacement to become bigger and bigger over time. So some examples of this would be rocking a car out of a snowbank. You have to kind of start, and then as you keep applying the force, and it has to be at a very specific time, right, in order to get that to keep applying, you can cause larger and larger displacement and get out of the snowbank. Another example is the Tacoma Narrows Bridge collapse. And here's the link, so we'll go to this. Okay, so obviously you saw that that bridge, it took a small amount of motion, but then it kept adding on, so it had resonance, which created this huge wave, which caused the bridge to collapse. So these are the problems that we're going to do in class. And then if it ever comes up. Okay, so these are the problems we're going to do in class, and if you want to start them, you're more than welcome to do that. And then here is the homework, and you also have the answers on your outline. Have a good day.